almost good afternoon. Today our talk will be done by Paolo Cipollini. Paolo Cipollini is an engineer and a satellite oceanographer. He has a long experience on this interface between the satellite data, scientific problems, and remote sensing. He started in Italy, and then thanks to Marie Curie, he moved to Southampton, and he spent around 26 years in Southampton, until 4 years ago he joined ESA in the climate change office, if I'm not wrong, and now he's a mission scientist with and he works in the interface between the European Space Agency with scientists, and he is working with two particularly exciting missions in which I've been involved in one of them, in proposing one of them, which is the Sst mission. And the other one is the Harmony, that from the perspective of high-resolution oceanographers, it's are really exciting. So, Paolo, if you want to come. Sorry. I forgot to mention that, as you've seen, all this week we've had a very important meeting, the GRIST meeting, which is a joint meeting between the main space agencies in the world, with NASA, ESA, EUMETSAT, the Japanese space agency, and so on. So we have discussed allowed us to make Paolo come and give such a nice talk. So please, Paolo.
Thank you very much, Jordi. Thank you very much, Christina, for inviting me. And it's a great pleasure to come here and have the opportunity, and it's a privilege to tell you about how the European Space Agency supports research for the ocean and for climate research and knowledge. So I will be covering a number of things. It's a presentation that I put together with the help from many colleagues, too many to mention, in different divisions of the European Space Agency, so it's spread over 3 different countries, ESTEC in the Netherlands, a climate office in the UK, and the data applications division. In fact, there's some help from the people in the ground segment in ESRIN in Italy. But throughout my presentation, which is really a talk to illustrate what ESA does for oceans and climate, I'll put in here and there contacts so that you've got them. They'll be on the YouTube recording. So the names of the colleagues who are doing particular things. So if you see something that you're interested in, you know who to contact, or you just come back to me and then I'll put in touch with them. So we support scientific research and application, and we support the user services. Very much everything that we do in Earth observation is driven by the users wanting data, wanting services, and providing ideas to us. So we do research and development, and I'll tell you about that. Physical principles, algorithms, observations, technique, very much R&D stuff. Even more recent things like artificial intelligence for Earth observation. You know, there's people in ESRIN doing a lot of that. Then the second thing that we do, in addition to research, we give you the data, the best possible data from satellite. And it's not just ESA mission, there's also Copernicus, the ESA-led missions, I would say, but there's also Copernicus missions, third-party missions. I will illustrate that. In particular for the example of climate data, but we could make many examples. And then, which is in fact what I'm particularly involved at the moment, in designing and implementing the missions of the future. So what do we want to do next? In response to the user needs. What we do is not by chance. You know, we listen to the users and we implement the missions of the future. In particular, we implemented the space segment of the Copernicus program, and that's the family of the Sentinels satellite that you'll be familiar with. But there's also things like the Earth Explorer family of missions, where we really empower the science community to do exciting new science on new cutting-edge topics. let's start from the first thing, research and development, and I'll talk about the Ocean Science Cluster. This is a network of ESA-funded projects, and we do fund a number of different projects promoting networking and collaborative research in ocean science. And this is to advance our knowledge of the oceans and also for climate. So the colleagues, Maria Lenrio and Diego Fernandez, are in charge of this. You can find a lot of information on the web, but suffice to say that we've got a range of different projects. These are research projects that ESA is supporting somehow, and they cover a number of areas of marine research having to do with oceans and having to do with climate. So I will only make a couple of examples here. You see in the top right, or rather in the middle on the right, we've got a number of projects having to do with the ocean carbon cycle and ocean fluxes like BICEP, ocean flux, they are also listed at the left here, Ocean Soda, BICEP, Aeolus Plus. These are a number of research projects that investigate pools, fluxes, and processes that influence the ocean solubility and the biological carbon pump. So we are involved in many stages of the ocean carbon pump there and the ocean carbon cycle. And that's just what you see here, this area, ocean carbon, but we've got other projects. They were named in the previous version of the slide that you see so a moment ago. On ocean extremes, we've got projects on ocean health, projects looking at what happens at the coast in terms of land-sea interactions, or projects looking at the air-sea interaction and the upper ocean dynamics, and finally looking at the ocean's role in the earth and climate system. So there's really quite a lot. I invite you to have a look at the Ocean Science Cluster. This is just to give you the flavor of, we support research and development because obviously everything else stems from that. But I told you that another thing that we do as agency, we provide you with the best possible data. We try to provide the best possible data that you can get from satellites. So I will talk about data using one particular program of the agency, the Climate Change Initiative, because I had the privilege, as Jordi said in the introduction, to work for a few years recently with the ESA Climate Office based in Harwell in the UK. And they run a program called the ESA Climate Change Initiative, which is aiming at maximizing the value of satellite data for climate research. So it follows the requirements from the climate modeling community and from GCOS, which is the Global Climate Observing System. And we run in the Climate Office, ESA runs 24 projects looking at ECVs. So what is ECVs? Those are the essential climate variables. So those are the fundamental variables that we use to monitor the state of the ocean. And you've got them all there. You've got familiar things like sea surface temperature, sea state, and so on. And it's not just the oceans. We've got a range of variables over land and a range of variables here on the right for the atmosphere, so greenhouse gases, aerosol clouds. For each one of those, we run a project to create the best possible time series of that variable using all available data sets that we got from satellites. So it's really the port of call if you're looking at data for climate research long term. And this is very much in response to the UNFCCC, the United Nations Framework Convention for Climate Change Requirements, that we launched this program in 2010 and is going on until now. And now, looking at the variables over the oceans, the work that the CCI, this climate change initiative does, provides then support to the IPCC special reports, like the one recent on ocean in cryosphere and changing climate. Many of the papers coming from the CCI initiative provide really the meat, the scientific meat on which those reports are based, and this one, for instance, has got results from sea level budget closure, ocean color, glaciers, ice sheets projects. I will be mentioning some of these projects in more detail in a moment. Just to iterate on the ESA contribution to the IPCC report, in particular from the oceanic side, there's in this Climate Change 2021, which is the latest assessment report, Assessment Report 6. Again, we've got many results that are coming from the Climate Change Initiative. One example is in the bottom left. The ESA CCI sea surface temperature is recognized as one of the primary reference observational data sets against which we monitor the performance of models, of climate models. So that's very important, because then you use those models to forecast what's happening in future. And let me tell you a little bit about, one by one, about the oceanic ECVs that we've got in the CCI. And you've got them all. We've got sea level, sea surface temperature, ocean color, and sea ice, which are a little bit more mature. More recently, we started sea state and sea surface salinity. And then there's a variable across CCV activity, quite exciting, combining many of those ingredients up there to close a budget, to close the sea level budget. And let's start, in fact, from sea level. We've been observing sea level from space, of course, since the early 1990s, with a string of missions in very good collaboration with other agencies, NASA and CNES, and also EUMETSAT. That's the curve of sea level from space. What we do in the Climate Change Initiative is to try to derive the best possible time series of that kind of global mean sea level from all the available data in the past, doing serious quality screening, revisiting the algorithms, and intercalibrating the various missions, so that we've got the best record of the increase in sea level from space. And we are working on algorithms, on generating the long-term observational records, and those standards set up by the CCI then are taken up by the climate services, Copernicus Climate Services, C3S, and the Copernicus Marine Service, CMEMS, to produce time series operationally, routinely. Of course, we see that it's accelerating. And at the moment, because the CCI is very much research-driven, we are looking at the next step, which is to go closer to the coast, because traditionally with altimetry there were problems in the coastal zone, so we are trying to extend the data records so that they are more reliable, still over the entire history of the data record since the early 1990s, closer to the coast. In fact, that's an illustration of the research and development of coastal sea level trends in CCI that I don't have time to go in there in details, but essentially the comparison between the altimeter data and tide gauges at the coast with revised algorithms to process altimetry is getting better and better. There's one example here from these two papers by Birol and then by Marcello Passaro et al. Where the agreement is quite good, but in general it's reassuring to see that the coastal altimetry, so extending altimetry into the coastal zone, is now an acknowledged, accepted mission objective for all the current mission and for all the future missions. So we've conquered the coastal zone. It's interesting to mention at this stage also the sea level budget closure, and I also say that Jérôme Benveniste is the contact point for these, for all these projects on sea level and the sea level budget closure. And this is where we, this is really the final proof that the results from different ECVs make sense, and they are very accurate, because when you combine them, you combine results on the contribution to sea level from the Antarctic ice sheet project, the Greenland ice sheet project, the glacier projects. So they are projects all looking at the variation of those domains in the cryosphere, and the thermal expansion from the sea surface temperature, CCI, and you combine them and you compare them with what you see from altimetry in terms of actual sea level. There's now almost a perfect match. So we closed the sea level budget, and it's really the proof of the pudding. Let me move on to sea surface temperature that my colleague Craig Donlon is following, and Chris Merchant, who was here this week for the GRIS meeting, is the principal investigator on this. And sea surface temperature is an incredibly mature data set where Chris and his colleagues have been able really to extract the best possible information from this very long time series of different missions, carefully intercalibrating them. And what you see there, that pulsating image, is the annual cycle of SST. It's a climatological cycle built with 40 years of data. So you see, in the day of for each day of the year, how the average SST is. And of course, the measurements capture the increase in the global SST. At the moment, this data set is also being improved with the addition of sea surface temperature from passive microwave, and also at the moment is based, the reference sensors in the data set are older missions, but we are moving into making FLSTR A and B, the infrared sensors on Sentinel-3 as the reference sensors. So there's more research still to be done to make these data sets even better. The next one is ocean color. I've got the pleasure of managing this on the ESA side, but now handing over to Roberto, my colleague Roberto Sabia. And ocean color, of course, reveals changes in ocean life. There's a longer history of continuously improving ocean color data sets, a long time series. It spans currently 23 years, and more years, of course, are being added, so it'll be almost 25 very soon. And it's a global merged product that has Envisat data from the MERIS sensor, and then with all the NASA missions. You see Aquamodis, SeaWives, and this is a very good example. We created this data set, really putting together all the data from all the different missions from all the agencies, and there's a very good interagency collaboration on this. And then, of course, there's OLCI on Sentinel-3A, and very soon we'll add the OLCI on Sentinel-3B. And in fact, we want to move it towards taking OLCI A and B as reference sensors. And the ongoing work, or recent work, I should say, is that we've been able to use the ocean color data set from the CCI to derive a biological indicator. What is an indicator? 1 minute ago, you saw the global mean sea level rise curve, which is very known to everyone as sea level rise. Well, that is, that global mean value that goes up in time is a good example of an indicator. So the variable, the ECV, is mean sea level. The ECV is sea level, but then when you integrate it and put it all together in a simple plot, you see the plot going up. That's a very good indicator. We are working on having something similar for the ocean biology, and a very good candidate is productivity, or global primary production, which is a measure of how the photosynthesis happens in the ocean. And this is influenced by a number of different phenomena. And the Ocean Color CCI consortium has derived a global primary production variable as an indicator. We are now also funding, and again, this is research and development to create a new data sets. So you see, the aspects of my talk are interrelated. An ocean carbon from space study kicking off this summer to improve estimates of fluxes and reduce the uncertainties in our knowledge of the uptake of carbon by the ocean. And my colleague Roberto Sabia is involved in driving this. Let's move to the cryosphere, or rather the interface between the oceans and the cryosphere, sea ice, where we see, of course, from satellite data, which we develop in close collaboration with the colleagues in EUMETSAT, OSISAF, a sea ice time series declining, and we've got 40 years of data there. This is led by Anna Maria Trofaier. And at the moment, we are trying to extend the time series, not just in the future, but even to recover more data from the past. Because to give a climate perspective, sometimes one very useful thing that you can do is not just to add the latest data, but also to go back and do some kind of the equivalent of archaeology, if you want, and try to exploit and reprocess with new technique and new knowledge old missions, so that you make your time series better in the early days, or perhaps you even extend them back in time. And now we're trying, for instance, to extend the sea ice thickness back to the 1990s with the ERS-1 and ERS-2, to very successful ESA missions with an altimeter on board. And this is just an illustration of, when you feed sea ice thickness information from the CCI in a simple sea ice model. Without it's on the left, with it's on the right, and you gain a lot of more detail, a lot more structure, a lot more realism in the output of your model. Another ECV, Sst, that's the wave field. And we've got a project, Sst CCI, where we have been deriving a time series of Sst from the early 2000s, and we can look at changes already. For instance, the different from the 2010s and the 1990s, with areas of the ocean getting stormier, areas getting more calm, which give an interesting climate perspective. And there's a new version of this Sst CDR. CDR is Climate Data Record, so the full time series, which is about to be released. And this one has got information from altimeters, or even from imaging SARS, which is a novelty. And I'm managing this one. Sea surface salinity, I'll just quickly mention here, because this center where I am today in ICM is one of the leaders in this particular CCI. And it's a fantastic data set where within the CCI program we've been able to take full advantage of ESMOS and ESA mission, but also Aquarius and ESMAP, NASA missions, and put them all together. And this is acknowledged even by our colleagues on the other side of the Atlantic, that a very good job has been done. Now we've got a long climate data record for the first time of high quality sea surface salinity with uncertainty, because if you want to feed the satellite data into a model, you need, if you want to assimilate it, you need to know the uncertainty associated to the satellite data. It's crucial. This merged data set is, of course, available like all the others, free to use. And like I said, it's of great value for ocean modeling and climate research. And in fact, indeed, this is just a gallery of pictures from a number of different studies that I have been using in the last couple of years, have been using this new data set from the salinity CCI, where the ICM and the Barcelona Supercomputing Center are very valuable partners, I should say. And Roberto Sabia is now following this one. I mentioned modeling, the CCI very much, with the data that we provide, interfaces with modeling, because we provide this data, these climate quality data records to the modeling group, and there's in fact a climate modeling user group which acts as the interface with the modeling world, and in fact the BSC, the Barcelona Supercomputing Center, is a project team there. And more recently, just to reinforce this message that what we are doing is crucial for climate, and we need to, and we really value the collaboration and the interface, the cross-fertilization between the Earth observation world and the climate modeling world. The International Project Office of CIMIP, which is the Coupled Model Intercomparison Project, is a project of the World Climate Research Project. The project office has been established at EXAT, that's ESA's base in the UK, where the climate office is located, and so that there is even more collaboration there. So, lots of data. You've got all of them via a very simple link, climate.esa.int. You see all the details on the projects, the ECV projects, and you can access the data. And the important thing is just, all the data are free. One very important thing that I would say is the 1, 2, 3 is the 7th bullet point there. Perhaps I should have highlighted that all the data in the CCI come with a uncertainty characterization. So you know the number, but you know also the associated uncertainty, which is crucial if you want to assimilate it. And the CCI is continuing. Susanna Mecklenburg, the head of the climate office, is leading now the proposal, well finalized now, to the ESA member states for the evolution of this initiative called Climate Space, which will focus still on the generating very good data, but also targeting more closely things like the global stocktake, the inventory of greenhouse gases, and the ESA agenda for 2025. This was just the example of the data that we do for climate. I could have spent perhaps another half an hour talking about the similar data, in some cases with similar algorithms, so the same processing chains, being provided to the operational services like the Copernicus Marine Service. Just to say that, that it's not just the climate perspective, there's also an operational, a strong operational oceanography perspective. And the third thing, the last thing that I want to cover in my talk is this thing on missions. The missions that we run. There's so many. the Earth observation missions, it'll be 90 in total. I'm sorry, the font it doesn't show. It's a fancy ESA font. It doesn't show well on a Windows machine. But we've got three main families. The science missions on the left, the Copernicus missions in the middle, and then the meteorology missions for which we support our colleagues in EUMETSAT, of course. And I'll be talking about just a few of them, just to say, with so many missions, look at just the planned launches of new satellites over the next 10 years. And we've got quite a number of the science missions in the top, Copernicus missions in the middle, and meteorology missions at the very bottom. And if you look again at this map, let me just start from this middle class. The missions that ESA develops for Copernicus, where we develop the space segment, so-called space segment. So the satellite and the processing, initial processing, then the operational is actually run by others. And the Copernicus context of mission at the moment is, as you see in this slide, we've got a number of Sentinels of the current generation. Those in blue are already in orbit. They've been already launched. You will have heard about the various Sentinel 1, 2, 3, 5P, 6A, and so on. Then there's more to come from that generation. In many cases, they are already in storage and ready to be launched to continue the constellation. Then we are developing at the moment a next generation of Sentinel. And then in recent years, it was apparent that we needed to expand the capability of Copernicus with some dedicated missions to cover some gaps. And here they are on the right. So it's interesting. I don't have, of course, time to present them all, but just going by broad families, and then I'll make a more specific example. But we've got imaging radars there, and Malcolm Davidson, my colleague, is in charge of them. Following on Sentinel-1, which has 2 in orbit, although Sentinel-1B at the moment is being fixed. It's got some problems, but Sentinel-1C is almost ready to be launched. And then there will be a next generation Sentinel, which is being designed at the moment. And then as a particular Copernicus expansion, there will be an L-band radar for Arctic and Cryosphere monitoring called the Roselle. And then we've got high-resolution, hyperspectral instrument, the Sentinel-2s, mainly for land applications, but very useful indeed over the coastal oceans in many cases. So Sentinel-2, again with the next generation, and also in the Copernicus expansion chime for the hyperspectral imaging, which will also be of great value in the coastal ocean, followed by Marco Celesti and Matthias Drusch. And then the altimeters on a reference orbit, the reference orbit for the sea level curve that was started in the 1990s that you've seen in my previous slide. We are continuing always on the same orbits so that there's no issues about whether some of the changes may be due to changing the orbit of the satellite. That time series is being continued by Sentinel-6A and Sentinel-6B that Craig Donlon is following. And let me just illustrate the beauty of Copernicus with all this, just taking 3 of those missions that you've seen in a previous slide, over a lagoon in northeastern Russia, and you've got on the left Sentinel-2B, so it's a hyperspectral image. In the middle you've got what you see from the radar, Sentinel-1B, that sees all the structures in the sea, and perhaps you can make up a little bit of the wave field, and it was actually taken in November, so you see some ice on that lagoon and all the different structures. And from the altimeter on the right, in this moment you see the low resolution altimeter, because we get low resolution data from Sentinel-6, which was the heritage old technique, but it's been improved these latest missions so that you can process it with advanced high-resolution SAR techniques, and what you get, you can almost use it as an imager, and you still see the frozen lagoon and the structure of the waves, and you see a river over there. So putting together all these things, we get an enormous potential to study all the different processes and to apply those data to operations. I'll make one example how things are evolving from the current generation to the next generation for the Sentinel-3 next generation altimeter. Sentinel-3 at the moment has both optical, infrared, and altimeter on the same satellite, but that's not really optimal. And for the next generation, we're splitting them into separate missions. So Sentinel-3, here they are. We've got A and B in orbit, and C and D due to be launched. With the altimeter on Sentinel-3, we get things like sea level rise, wind and waves, sea surface height, and we use it for tides. Sentinel-3 goes to 81.5, almost 82 north and south, so we get observation for sea ice and ice sheets. I don't need to repeat that. These are observations in the polar oceans. You see there's a gap because it only goes to 82, but still we see a good, almost entire Greenland and quite a little bit of the Arctic. Now, with the current constellation, to make a long story short, the problem is that we have with altimeters is sampling. So they are good. We see a lot of very good parameters. You've seen them before. But what we would like to do is to improve the sampling. So the combination of spatial and temporal sampling is never enough for the observations that you want to do. And in fact, with Sentinel A and B, after 5 days, you only get those tracks. And so, there's quite a lot of gaps and so on, and people have been studying, combining all the altimeters that we got at the moment, what is the effective spatial and temporal resolution, and it's not too big. This has been done in a number of virtual stations. It's of the order of, 1 month, so on, and spatial resolution of the order of a few hundred kilometers. So how do we improve on that? Even considering that we can use altimetry to look at hydrology. And so we have more requirements coming from hydrology, looking at rivers, and they are also telling to us the same thing. Oh, yes, the altimeter is very good. I can monitor the level in the river, especially in remote regions like Congo. But once every 10 days is not enough. I really would like to see it more often. So we've got this big requirement. 10 days sampling of the current altimetry missions is not sufficient when you look at river levels. And sampling is this fundamental requirement in space and time. So these requirements have been captured so that we need to improve sampling and coverage. And let me just skip, because in the interest of time, to the result. We are now developing the next generation, and the next generation is an advanced concept where we could use SWOT altimetry, which gives a 2D dimension to altimetry. So a constellation of 2 or 3 SWOT altimeter satellites like you see in there, which has been covered by SWOT, a NASA CNES mission, or a constellation of many up to 12 native pointing altimeters, or perhaps a combination of the two. So this is just an illustration without going into the details. An illustration that based on a requirement that we're getting from the users, they want more resolution, we evolve the constellation so that we try to respond to that requirement. And it's happening the same for the others. Let me just tell you very quickly about the Copernicus expansion missions, and those are the 6 new missions that will extend the capabilities of Copernicus. I'm following in particular Crystal for the addressing the monitoring of the cryosphere, because this one goes almost all the way to the pole, 88 north, so it will almost fill this hole at the pole with altimetric measurements that allow us to compute ice volume and so on. And again, to show you how we are trying to do things better. One problem that you do when you measure sea ice is that with sea ice, there's a very simple formula. You measure the level of the ice in the cracks, of the water in the cracks between one ice floe and the next one. You measure the level of the ice, and that height, that difference, what we call the freeboard, is related to the thickness. So you can compute the thickness nicely. Now, if you have snow on top of that floe, things get complicated, and you cannot use the same formula. So ideally, you also need to measure the thickness of the snow layer on top, otherwise your sea ice thickness is not correct. And in fact, Crystal will measure snow depth, and we use a new concept of adding another band. So we use a KU altimeter and a KA band altimeter on the same platform, sharing the same antennas, indeed, and this will give us a much improved view of sea ice, and it will still allow monitoring Antarctic ice sheets. And I'm not forgetting that here we are talking about the oceans. As secondary objectives, we will still get ocean surface topography, sea state, and coastal and inland water levels from Crystal. Let me just skip this. And finally, the explorers. These are science-driven missions, because so far I've shown you all Copernicus missions, but these are really the ESA-funded science-driven missions that do exciting new science. And we've had there's 9 explorers already, 5 already in orbit, and they've been extremely successful. Think about Cryosat. You might have heard about Cryosat, providing really a lot of very good observations, even for oceanography, which indeed will be continued by Crystal. So an explorer then is followed on by an operational mission. And I like to briefly mention, because Jordi is interested in particular in those two, the next 2 explorers that I'm I should say in preparation. Well, the Earth Explorer 10 Harmony is a candidate mission. Hopefully next week it will become a confirmed mission for implementation, because that's a crucial user meeting that has a passive SAR, so it follows one of the Sentinels 1D, for instance, and it's made of 2 satellites following on the same Sentinel track and getting the reflected SAR echoes. And it also has a multi-view thermal infrared instrument, and is extremely powerful in terms of what it can resolve for a number of applications, not just oceanography, but even for the dynamic Earth and so on. And I've got there on the right things that you will be measured by Harmony, SST, cloud top motion, roughness, Doppler, and so on, and applications that include the sea ice dynamics and ocean atmosphere coupling, so very important. And then one of the 4 candidates that we've got now for the following round of the Earth Explorer 11, is SeaStar. Jordi has been involved in this one also. And this will be a mission to measure directly currents at the surface of the ocean. It uses a technique called squinted along track interferometry. And look at those numbers in blue. It's a mission that aims at measuring the total surface currents with an uncertainty of less than 10 centimeters per second at 1 meter resolution. So we should be able from space to measure currents with that resolution. And it uses 3 radar beams, one looking forward, one looking to the back, and one looking on the side, putting together all that information for measuring the currents, and indeed also there's a wind product from SISTA. So you see, this is still in competition with 3 other missions, so it's not, we're not sure that it'll be selected, but it's certainly a very good example, the cutting edge new missions that we are developing. And I'll finish off my last example on a small class of missions there. You see, I'm still using our full scenario of missions. I really would like to mention one of those 2 there, because it's an interesting concept. Those missions are the scouts. We call them scouts. It's a class of missions. And hydrogen is one of those 2, measures the reflections of the GPS and GNSS signals to do Earth observation. And you can look at a number of different things using that concept, including, and I've highlighted in blue there, as a secondary object, but still important for us, ocean wind speed and ice extent. The National Oceanography Centre in the UK are working on that. You've got the contests there. This is very much led by the Surrey Satellite Technology Limited, who are the prime in the industrial consortium. And this is going ahead. This is being built. I like to mention this class of missions, scouts, because these are very agile mission, low cost. The budget for this is 30 million euro, whereas for the typical Copernicus mission that I mentioned before, we are talking about 1 order of magnitude greater, 300 million, 250 or 300 million. So we are trying to build this with a budget of 30 million euro. So for instance, using a lot of components off the shelf. So you don't develop new components, new electronics and so on. You buy what's available on the shelf. And it was starting in 2021, and we're aiming at launching it in 2024. So it's a very compressed thing. So it's nice. We do not only do the big things, but even small exploratory missions like that. What do you get from all this? My final slide, you'll be pleased. My take-home message. I hope I've convinced you that what we do in support of ocean research for ocean research and climate research is 3 things. So we enable the R&D, lots of projects supporting the R&D. We provide the best data. We put together different missions. We go back in time. We refine the algorithms. We want to get the best time series, the best data for your application. Both climate application, operation application, near real time throughout the Copernicus marine services and so on. And then we prepare the missions of the future of all sizes, operationals and research and so on. So that's what we do. Now, I like to stress that of course, why we do this? We do this to advance scientific research, to provide tangible societal benefits. That's what we do. But we do this, and this is crucial, with scientists. We do that with science, and the scientists are central to our work. Because, I'm asking you to engage, to work with us, to advise us. We get your advice and we go forward. So show us how to better respond to societal needs. Show us what to explore next. Those scouts or the Earth explorers, they are all coming up from ideas, born and bred in the scientific community. And that's really, your help. We need you to tell us where to go next. So please engage with us and tell us where to go next. Thank you very much. good.
Thank you very much for your talk. I understand that later this year there's going to be a launch of a mission called SWOT by NASA and the French Spatial Agency. Is ESA somehow involved in that?
Yeah, we collaborate with them.
Because that will give high resolution altimetry data, right?
Exactly. And I apologize that perhaps I didn't stay on that slide too long, but it was mentioned when I showed the two solutions that we are contemplating for the evolution of the Sentinel-3 next generation topography. One of them is indeed this combination of two or more 2D altimeters, which are done with the same principles of SWOT, and we are really looking forward at getting the results and the data from SWOT to refine the algorithms and see to what extent we can import that technology into our constellation. At the moment, just to tell you that we are considering this, the idea is that we could start launching a constellation of traditional altimeters. So we would have a hybrid solution where we first launch the constellation of the traditional altimeters, and then one by one we add some SWOT-like instruments as soon as we see the results from SWOT, and we can optimize the design. So we learn from SWOT, which will be a pioneer mission in many respects, and so that then we can integrate it in the Sentinel-3 next generation topography constellation. In fact, we are referring to this evolution, the evolution of this particular mission as a topography constellation, because it's very likely that it will be a combination of different satellites, perhaps a handful of satellites with two different principles, two different operating techniques.
Okay, I had a sort of like a follow-up question or comment, because I don't know much about satellites, but at one point to gain spatial and also temporal resolution, but for a specific site, you can contemplate, I guess, geostationary satellites, right? Is that still feasible or not? And then also for oceanographers working on primer production and so on, it's very important if we had on the same platform or whatever, both ocean color and altimetry data to have the fluxes at the same time that you have the chlorophyll in there and things like that. Is that,
exactly.
I'm speaking out of ignorance. Is that all that possible?
No, it's what you say is true. For the synergies, we would like to have altimetry, ocean color, SST, all at the same time in the same place. And indeed, perhaps even the kind of surface current, high-resolution surface currents that we hope we will be able to get from SeaStar, from something like SeaStar. And prior to that, observations from Earth Explorer 10 Harmony. So the problem is that, let's take the current Sentinel-3 generation. It has altimetry, ocean color, and sea surface temperature on board, all on the same platform. In terms of synergy, is a good example, but unfortunately, the best orbit for altimetry is not the best orbit that you would want for ocean color, sea surface temperature. And that's indeed the main reason for which now they are sort of going separate waves. And the idea is that we go separate waves, but we try to maximize the sampling and the coverage and have more of them, so that at the end, even if they come from different platforms, then at the end you will still be able to put the data together and do very good synergy.
Any other question? Okay. Well, I have plenty of questions and comments and so on, but just a very quick question.
Shall we go for lunch together?
Yes, you're right. Just I'm thinking about to which extent the fact that For Earth Explorer 10, Harmony, it will be, as far as I understood, it will be accepted for the next phase and so on. How this could affect the Sst mission? Because at the end, they are quite overlapping.
No, I would not agree on that.
Okay.
They've got a rather different mission profile. Harmony is very much, because I only went through it briefly, but let me say that again. It's a pair of passive SAR that have to be used in combination with one of the Sentinel-1B. So it's very much constrained by the orbits of Sentinel-1D in particular, which is the Sentinel that they should be paired with. For things like currents, the resolution that we expect is of the order of 25 kilometers. Whereas Sst is a mission which has a completely different mission profile. Initially, it will be launched on a daily repeat orbit. So over the globe, you will only have a number of tracks, but they will be repeated daily to look at very fast processes. So you will have this mapping of currents every day. And then it will be moved to a different orbit to map, with a revisit time of about one month, the whole of the world's coast. So the whole coastal zone of the ocean. We cannot do it global. It's not global. It couldn't be global because there would be problems in the amount of data and the radar duty cycle, and it could.
So since Harmony is expected to have these ocean currents or Doppler measurements at around 25 kilometers, I understand that there is no plans from ESA to add the Doppler capability to the scatterometer, like Wacom in the USA.
No.
Yes. Okay. Any other question? No, I think it's
no, to the benefit of the colleagues in the online.
All right. Thank you. Thanks. So the feasibility of snow depth estimation, Pan-Arctic, that's been recently, at least the potential shown with combining ISAT-2, which is a laser, and Cryosat-2, which is microwave. You mentioned there is a Ku-Ka band mission coming up?
Yes.
In the works. Can you say something about the pros and cons of using laser microwave on the same platform, which is not what is being recently shown, and using Ku-Ka band, so microwave to microwave laser? What are the pros and cons of that?
Well, the current experiment in combining laser and microwave is indeed the Cryo-2 experiment. Let me say a few words about that. There's this beautiful mission, US mission, ISAT-2, which is a laser altimeter. So laser altimeter works wonders and really captures normally the very top of the snow layer. And we've been, in the past year or so, we've been slightly moving the orbit of the current Earth Explorer Cryosat, which is an aging mission. It's been there already for 12 years, but it's still working extremely well, so that Cryosat, the altimeter, and ISAT-2, the laser, would be every so and often almost going in parallel on the same orbit within a few hours and almost covering the same track. And so that we've been able to combine those observations. The laser that gets to the top of the snow layer and the Ku band altimetry, because Cryosat is only Ku band, that goes in depth and ideally should capture the interface between the snow and the ice. And the results are extremely encouraging, in supporting the case for crystal, which is an altimeter where Ku and Ka will be on the same platform, and having a Ka band radar, which should get to the top of the snow layer, essentially gives you as an advantage to the laser that it's an all-weather instrument, so you can always take your measurement. But I really would like to stress that very much the support, the evidence that we've got that the crystal works comes from a number of experiments, but very much also from this combination of laser altimetry and radar altimetry that we are having from the Cryo 2-Ice experiment.
Can I ask a follow-up question? So, yeah, thanks so much. So I guess what you're saying effectively, Ka is like a laser in the sense that the skin depth of snow is 0 for
Yes.
Ka, and therefore it's both on the same.
Let me tell you the beauty of all this. So in principle, but I'm idealizing,
Yeah.
in principle, and I'll go back to a slide that I skipped because I want to put it on now. It's very relevant to this. In principle, Ka is reflected at the top of the snow, and Ku penetrates the snow layer and gets reflected to the snow ice layer. In practice, there's quite a lot of happening, especially a Ku band in terms of volume scattering, and also Ka penetrates a little bit in some volume scattering. So, on building on the evidence that we've got so far, which makes already a very good case for a mission of that kind for crystal, which is going ahead, we are aware that there is still a lot of work to be done on the improvement of the algorithm, but it is exciting research that we will use, we will exploit, and ideally perhaps we will also be able to resolve somehow the structure of the snow layer and then of the ice layer. For instance, when they are melt events, very warm summers, and then the following years the ice keeps growing because more snow gets on top and it's then compacted. Then in the ice you've got a very reflective layer deep down due to that past summer where you had a very, very wet surface that has really almost completely melted. And we see those things in the in situ radar data that are collected. Last year we ran this workshop on the state-of-the-art in multi-band altimetry of the cryosphere. So if you Google dual cryo, there's a workshop report, and we also looked at what we are having at the moment from the combination of laser altimetry and Ku altimetry. There's also a Ka altimetry in orbit, so in some cases Altica, there's a French-Indian mission, extremely successful. So in some cases we've been able to combine laser from ISASat-2, Ku band from Cryosat, Ka band from Altica, although not always with a very good match-up in terms of time, but there's good evidence that, by putting together information in different bands, you gain quite a lot in knowledge. The main problem with laser is that the laser is extremely power hungry and doesn't see through clouds. So crystal will go ahead as a Ku, Ka band altimeter, which is an all-weather instrument. It should give remember crystal is operational, so we believe that, developing, following the good experience that we've got for Cryosat, we can have a very good, sustained, reliable set of observations to build sea ice thickness maps operationally.
I've been given the mic, so I don't want to give it up. I don't want to take over, but can I make another question?
Oh, please.
Well,
you're very
I don't
welcome.
want to make it too long. So altimetry relies critically, or depends critically on precision and precise orbit determination.
Yes.
And you're talking about the next generations there. And, to do POD, well, you need a reference frame, a stable, accurate reference frame. And in fact, mostly, not so much for altimetry of the troposphere, but yes, for sea level rise, right? So you need to know what's the error of the reference frame and the estimate of the sea level rise.
Yes.
Is there anything within ESA to support the reference frame, and that means on the ground, and that means, how well one knows XYZ and XYZ dot, the velocity on that?
Okay, that's a very good question. I'll need to refer you to other colleagues who are looking in particular at those issues. So perhaps we'll follow on, after the talk. But let me just say that it's a very pertinent and legitimate question. The only partial information that I can tell you is that, of course, Crystal will have the usual set of tools on board to do precise orbit determination. So the usual combination of laser retroreflector and GNSS receiver, which will use also the Galileo signals. Of course, now we've got Galileo. And we are also now discussing the opportunity of also adding a payload as an extra little payload, a Doris receiver, which is the other system for orbit positioning. So we should be properly set up to do orbit determination to the same level of accuracy, the same level of uncertainty, I should say, that we see with the Sentinel-3 and Sentinel-6 missions. But for the particular issue of the reference frame, I'll have to put you in contact with the colleagues.
Any other question? No? I just would thank you and just give you, in support of on your call for the implication of scientists with ESA, I would suggest that here we are a huge institute with a lot of biologists working in the institute, and I think that one of the challenges that we have is that you, the biologists, also contribute to these missions. Now in Barcelona Expert Center, we have started, we have some people involved in optical measurements. So I think it's a great opportunity to start to strengthen this collaboration from you with remote sensing scientists. That's what I would say, because the other one, we are involved in sea surface temperature, we are involved in almost most of the missions of ESA. So what we are missing is this optical part. Well, anyway, thank you very much.
Pleasure. Thank you for coming.